Today we are going to talk about metric space, but I don't want to introduce metric space like a textbook. A textbook usually says let the whole space be a set and let D is x times x to real numbers satisfy three axioms, and then many students immediately think, okay, so today we are collecting another definition of the final exam. But that is not the point. The real question is, why does mathematics need distance in the first place? Because in the real world, nothing is perfectly exact. Measurements have errors, data points move, physical systems fluctuate. Even when you record a video, the audio may be too loud, the camera may be too dark, and your computer may have only 70 GB left. So the world gives us error. And the mathematics ask, can we make an error controllable? That is the beginning of metric space. Last time we talked about topology. Topology, we say that topology gives us rules for open sets. So open sets have to behave nicely. The empty set and the whole space are open. Finite intersections of open sets are open, and arbitrary unions of open sets are open. But there is still a problem. Topology tells us the rules, but it does not tell us where the open sets comes from. It is like saying, here are the traffic laws, but then someone asks, okay, but where are the roads? So today we ask, if open sets are the language of nearness, what products produce this language? And one very natural answer is distance. Let us begin from reality. Nothing in the real world is perfect exact. When you measure something, there is error. When you collect data, the data move. When you study physics, statistics fluctuate. Even in everyday life, if someone says, I will arrive in 5 minutes, mathematically that usually means somewhere between 5 minutes and the head depth of the universe. So exactness is not how it really appears to us. Reality gives us approximation. Reality gives us uncertainty. Reality gives us fluctuation. So mathematics is not escaping reality. Mathematics is trying to stabilize it. That is very important idea. Abstraction is not running away from the world. Abstraction is how we build structures strong enough to control the instability of the world. So now mathematical question is, what does it mean for two objects to be near? For real numbers, this is easy. If we have two numbers x and y, I can measure their distance by absolute x minus y. If the distance between x and y is small, then x and y are close. But what if the objects are not just real numbers? What if they are points in a plane? What if they are functions? What if they are probability distribution? What if they are physical states? Then we still want to say these two things are close, but now we need a structure that tells us what close means, so the world gives error. Mathematics must make it controllable. That is the job of distance. A distance function assigns a number to 2 points. We write d of x and y. And the mean is simple. How far is x from y? But structurally, this is more than a number. It is device that let us compare objects. Before we have d, the set whole space is just a collection of things. Maybe the whole space is a set of points. Maybe the whole space is a set of functions. Maybe the whole space is the set of possible states. But without distance, the set does not know which objects are close and which objects are far away. A distance function gives geometry to a set. It turns a naked set into a space where error can be measured. That is already a huge upgrade. A set says, here are the objects. A matrix says, here is how these objects relate by closeness. Now, if distance is going to measure error or closeness, it should obey some basic rules. First, distance should not be negative. If your GPS says you are negative 3 kilometers away from Starbucks, either your GPS is broken or you have entered a new branch of physics. Also, zero distance should mean the 2 points are actually the same. Second, the distance from x to y should be the same as the distance from y to x. Third, this is a triangle inequality. It says going directly from x to z is no longer than making a detour through y. This is not just a geometry fact. It is an error control principle. If x is close to y and y is close to z, then x should not be completely unrelated to z. The triangle inequality is what makes closeness stable. Now we can finally define a matrix space, but notice the order. We did not define it because the textbook told us to. We define it because the world gives error, and we need control. A matrix space is a pair, where the whole space is a set and satisfy the three actions we just discussed. So the whole space is a universe of objects, and D is a rule that measures how far two objects are. This means a matrix space is not just a set with a formula attached to it. It is a structure for making error controllable. That sentence is the main idea of today. A matrix space is a structure for making error controllable. If you remember only one sentence from this page, remember that one. Once we have distance, we can define an open ball. B sub epsilon of x is equal the set y in x, the d of x and y is less than epsilon. This means all points whose distance from x is less than epsilon. In plain language, all points sufficiently close to x. This is where the epsilon idea from limits comes back. In calculus, when we say epsilon greater than 0, we are talking about a tolerance. How much error are we willing to allow? The open ball is a region of allow error around x. So if y is in b epsilon of x, then y is close enough to x within the tolerance epsilon. That is why open balls are so important. They turn distance into local neighborhoods. They are the atoms of nearness. Now we can define the open sets. A subset U is a whole space. The subset is open if for every point x in U that exists some epsilon greater than 0 such that the B sub epsilon of x is a subset of U. What does this mean? It means every point inside U has some room to move without leaving U. If you are inside an open set, you are not standing exactly on a fragile boundary. if you wiggle a little bit and still remain inside the set. This is why open sets are the natural language of stability. If a point is an open set, small perturbations still stay in the same region. If real life terms, if your answer is acceptable and small error keeps it acceptable, then you are inside an open region of tolerance. That is why open sets matter. They describe safe zones for movement and approximation. This is a key of bridge of today. This is a structure chain. Distance gives us a way to measure closeness. Open balls describe local region of closeness. Open sets are regions where every point has local room. And the collection of these open sets becomes a topology. So now topology no longer feels like a random list of rules. It has a source. Distance produces some open balls. Open balls produce open set. Open set produces topology. This is how metric space generates topological space. Here is the theorem. Let XD be a metric space. Let tau sub D be the collection of all the open subset of the whole space. Then the T sub D is the topology of A on X. This theorem is a bridge from distance to topology. It tells us every metric space naturally becomes a topological space. So metric spaces are not separate from topology. They are one of the most important ways to create topology. Metric space is the concrete model. Topology is the abstract structure extract from it. This is very common pattern in mathematics. First, we understand something concrete. Then we extract the structure. Then the structure becomes powerful enough to apply far beyond the original example. Let us not do a long formal proof here, but let us understand why the theorem works. First, empty and the whole space are open. The empty set is open because there is no point inside it that can cause trouble. This is a classical mathematics strategy. If nobody is there to complain, the condition is automatically true. The whole space is open because every ball around every point is still inside X. Second, finite intersections are open. Why? Because if a point is inside two point sets, each set gives us some safe radius. To stay inside both, we take the smaller radius. That is why finite intersections use the minimum. Third, arbitrary unions are open. If a point is inside a union, then it belongs to at least one open set. That one open set already gives a ball around the point, so arbitrary unions do not need a global minimum. One open set is enough. This explains why topology allows arbitrary unions but only finite intersection. That rule is not random. It comes from a local neighborhood's behavior. Why does this matter? Because metric space gives non-vertical closeness. It gives actual distance value, but topology extracts structure closeness. It forgets the exact number and keeps the open set structure. So we move from metric to numerical closeness, topology, structure closeness, and continuity. This is important because continuity will mean a function preserves this structure. It's simpler language. If two inputs are close, the outputs should not suddenly explode apart. Continuity is the mathematics of stable transformation, and this is why topology is so central. It gives us the structure that continuity is supposed to preserve. Now here is the visual point. A metric space remembers exact distance. It knows whether distance is 1, 0.1 or 0.00001. But the topology remembers something more qualitative. It remembers which motions are safe. It remembers which points are neighborhoods. It remembers which regions are stable under small movement. So topology is not less geometry. It is geometry after forgetting numbers. That sounds strange, but it is powerful. Sometimes forgetting information is not weakness. Sometimes forgetting information reveals the structure that was hidden behind the numbers. In mathematics, abstraction often means forget what is unnecessary, keep what is structurally essential. Matrix remembers to measurement. Topology remembers the pattern of nearness. So today we learn the structure appear because problems demand them. Metric space appear because the world gives us error, and we need a control approximation. Distance gives open box. Open box gives open set. Open set gives topology. Next time we ask, which function preserve openness? It leads this to continuity. And eventually, this connects back to measure theory. This is a bridge we are building. A sigma algebra tells us what can be measured. A topology tells us what it means to be near. A matrix tells us how to numerically control error. And the Borel sigma algebra is where topological information becomes measurable information. That is why this matters. We are not just collecting definition. We are learning how mathematics turns unstable reality into stable